Hello, everyone. Thank you for joining our session today. We are going to talk about a very interesting topic. My name is Yaron, and I'm Senior Engineering Manager. And here with me, Kevin McGee, a Principal Engineer, and we are both from the ElastiCache team. So today, I'm going to start with introduction to ElastiCache and Valkey. And later, we're going to dive deep together on some advanced use cases and data modeling that I hope that you're going to benefit from building your application. So for those of you who are not familiar with Amazon ElastiCache, ElastiCache is a fully managed service that makes it easy to deploy, operate, and scale the in-memory data store on the cloud. Now, ElastiCache improves significantly the performance of your application by providing a microseconds response time. We support 3 open source engines. We started with Redis open source, Memcached, and Valkey. Valkey is open source, high performance, key value data store. It was forked from Redis open source last year when Redis changed the license. And last year we also announced that ElastiCache and MemoryDB support the Valkey engine. So today, all the example will be based on the Valkey engine. And to make it even more fun, we decided to build together with you an application so we can understand together how all this data modeling can help us to build a highly scalable application. So Kevin and I choose to build together with you a massive multiplayer online game. We definitely need to have highly scalable technology to support that. We need to make sure that we are providing a very low latency and high throughput to our customers so they can enjoy the game. So let's start from caching, because caching is the fundamental to make your application to run much faster. But I want to start with some high-level concept. So let's assume that we start to build our application on EC2, and we have the persistent data stored on some relational database. I'm using here RDS. So as long as our data is going on a steady state, this architecture can work well. But when we start to see more workloads kicking in with read and write throughput, we have multiple options. One of them is to scale up our RDS or to add more replicas so we can scale out and benefit from read and throughput using the replication itself. Now, RDS itself has the caching layer, but it keeps the caching on pages and blocks that does not contain the result itself. So from time to time, you need to fetch the data from the disk itself, and there is some additional latency that involved in that. For that, we can choose the Amazon ElastiCache that explicitly store the data in memory. And once we start to populate the result into the cache, immediately we can start to read the data from the cache itself and to improve the query response time and actually to receive a microseconds response read time. We can also relieve some pressure from the backend and from the database itself, and we can optimize our cost by allowing the backend to scale down. Now, let's move forward and see more advanced use cases. I want to start to talk about lazy loading, which is one of the strategies to handle a cache. And I want to show you how I'm managing that together with invalidation to the cache itself so we can make sure the cache stay fresh and without a stale data. So I'm using Amazon ElastiCache, and I'm starting to read the data directly from the cache. If we receive the data, if the data is there, we have cache it, all is good, we get that in a microseconds response time. If the data is not there, we have a cache miss, then we need to go to the persistent layer, the storage itself. Here I'm using Amazon DynamoDB, and right after that, I'm updating the data into the cache. So this is the way I'm lazily populate the data, warming the data upon every read. Now, let's assume that one of the items now has been up to date. And what we are doing here, I want to make sure the cache stay valid and have the no state delta. And for that, I'm going to use the trigger function that I have on the Amazon DynamoDB and to trigger a lambda. The lambda responsible to invalidate the specific item on the cache so we can make sure that next time on the lazy loading on the same path, we're going to update that data. Now, sometimes we have a very hot data in our cache. And we also use a time to live because this is the best way to manage our cache memory. And we want to make sure that the data is also evicted from time to time. So we're going to use expiry. But if we have a very hot item on the cache, we still want to make sure that we have the way to update the time to live before it's got expired. So we can benefit from keep reading it from the cache itself. And for that, we can allow some background task to update the data before it's going to expire. In my example here, I'm using Valkey multi-command. And the multi-command actually queued multiple different commands and executed atomically on the server side. What you see here, I'm using the get, first to receive the item itself, and then I'm checking what is the expiry time that left for this item. Now, in different example, as you can see here, we have multiple clients that get slowly listening the expiry until I'm going to get the last client that crossed the 5-second threshold and is the one that's going to update, to update the data on the cache to make sure that we have more expiry period for this hot item. Now, as a connected to that, there is the turn-the-read head problem that we want to avoid. This problem occurs when multiple processes or threads attempt to proceed simultaneously, often resulting in high contention and resource strain or a bottleneck. And this is something that we want to avoid. So let's assume that I have a very hot item on my cache that's about to expire. Now, if all my microservices will try to fetch the item from the cache now, they all will receive a cache miss. What eventually will happen, they all automatically, all together, will go to the database and will put much more pressure on my RDS. And eventually, we're going to impact our latency. And this is something that we want to avoid. And for that, we can build kind of barrier, a synchronization mechanism that allow only one of the clients to request the data from the database itself, and only him going to update and to populate it into the cache. So once he finished, and when all the other is waiting for him, we can read the data and receive a cache hit. So how we do that, how we build that? Let's, for that example, I took only 2 microservices, and I will go step by step and follow you how we can build it together. So the first microservice tries to fetch the item from the cache, but the item is not there, so we're going to receive a nil. The second microservice now is a bit slower, try to fetch the same item, it will receive a nil as well because the item is not there. Now, the first microservice will try to acquire a lock. I'm using here the NX and the EX arguments, which means that NX, if the lock already exists, I should fail. And EX means that I'm going to expire the lock after 5 seconds. It's successfully, because the lock is not there, I was successful, able to acquire them. And then I'm starting to query the data from the database. Now my second microservice tried to acquire the lock. And remember, because I'm using the NX, I'm going to fail because the lock is already there. Now what I'm going to do, I'm going to wait until the lock will be freed. So I'm waiting periodically until the lock is freed by the first microservice. In the meanwhile, the first microservice finished to fetch the item from the database, is going to populate it into the cache and free the lock. After that, my second microservice will be able to continue and to fetch the item from the cache itself. Another advanced approach is the client-side caching. That means that if I'm even more sensitive to latency, I can use my local cache to serve my on-demand workloads, which means I can benefit from very low latency capability. So for that, we have multiple ways to achieve that. First, the idea is very simple. We are fetching the item from the remote cache. Once we receive it, we store it on the local cache. And from that point, I don't need to talk with the remote cache because I can serve the items, the request for my local cache. But there is a problem. I need to manage now the data, the freshness of the data on my local cache. One approach is to use the time to live, the expiry that I can put on my local cache. The second one is to subscribe to the remote cache and to receive notification upon every changes. So let's see how it works. The first and the default approach of Valkey is to remember to store all the data, the mapping between the clients and the keys that they accessed. And every time we change one of the keys, I have the data stored in my Valkey, and I can update the specific client. This is very efficient, but from the other end, we need to have additional memory to store on my server side. The second way is to subscribe to a prefix. In my example here, I can subscribe to user as a prefix. So every time any microservice that's going to update a key with the same prefix, I'm going to receive a notification on that. So how I'm going to implement that on my client side? First, we recommend as a key principle to use a connection pool, a long-lived connection. The reason for that is because creating a TCP connection is an expensive operation, specifically if you compare to Valkey get and set, which is in order of magnitude faster than creating a connection. Additionally, using a client connection pool with a finite side reduces the overhead of connection management, and it's also bound the concurrent incoming connection from the client application. So what I'm doing here, I'm splitting my connection pool to two types. I'm going to have connection 0 as the invalidation connection, the control connection, and all the rest from 1 to 9 going to serve as the data connections. Connection 0 will subscribe to the invalidation channel, and all the other connection will perform the tracking on redirect on connection 0, which means that connection 0 will encapsulate all the invalidation to all the rest of the connection. So let's assume that I'm updating one of the keys. Immediately, connection 0 will receive that update on the invalidation connection with the specific item, and we'll make sure to update the data on my local cache. Now, sometimes we are thinking how to store the data on our Valkey engine. So it's very rich. We have a lot of ways to store the data there. I want to talk about two types because in my example, I want to store some session information. I will start with hash data structure, which is a very common data structure to store session data. It's very simple because it's mapped between key and value pairs, and we have the key that map that directly access to the cache itself. So in order to create the hash itself, we're going to use the hset command, and we're going to provide him the hash name and a list of pairs of key and values. We can also benefit from a very fast random access in a constant complexity to receive a specific item from the cache itself. Let's go through a simple code to see how easy it is to use that. So here I'm using a Valkey glide to connect to the Valkey server. And I'm generating a session, and I'm using the native hash map that I have on my Python to use the hash map. Then I'm generating a UUID that will serve as the session ID. Later, I'm going to use the hset command, the Valkey command, to serialize the hash data and using the session ID itself. To receive the data from Valkey, I just need to use the session ID that I generated, and I'm going to use also the hgetAll command, and later I can serialize it to my local object. Very simple. A different data structure that we also recommend to use is a JSON, very popular. So JSON is a data structure that consists of two main objects, array and key value pairs. In this example, I'm creating the JSON document using JSON.set. And I can simply use the JSON path to retrieve specific items from the JSON. I can use it to retrieve it from the array itself or from the upper level of the JSON. I also can use the array append to add additional item into the existing JSON very simply. Let's go through a simple code to see how it works. So I'm connecting here to my Valkey server, and I'm creating the JSON document at the beginning. Then later, I'm receiving the email of one of my users, very simply. And same, I'm doing that to retrieve the age. And I can also use the increment number to increment one of the indexes in my JSON itself. So what is the main difference between them? JSON usually used for a nested document, while hash is a key value pair for more simple objects like a session store, while with JSON we can use it for more complex one. Now JSON supports the JSON path to filter on the server side, while with the hash we need to do it and manipulate it on the client side. But both of them we can modify the items on the server side. So we announced a few weeks ago the support of semantic caching on ElastiCache, which can also retrieve one of the best performance for vector search in a high ratio of recall, of 95 recall. So to understand the semantic caching, we first need to understand the vector embedding. You can think about translating unstructured data like documents, videos, audios, images to representation of your data. Now, the vector embedding captures the semantic relationship between the different semantic elements. For example, with text, the semantic awareness of a word like a book can be sometimes when we read in a book and sometimes when we are reserving something. So to process the create vector, we involve ingesting data from the source, splitting it to chunks, and then converting it to vectors. So let's assume that we have a chatbot or some other application in our game, and we want to get a query prompt from the user. So we will use the same example like I mentioned before, like a book, but I'm going to add the furniture and finance here. And we will, again, visualize it with only 3 dimensions, only for the simplicity. So let's assume that we already have a question on our vector that say, how long do I have to wait for the next quest? And then I'm receiving a new query that said, when does the next quest start? So the cool thing here is that the semantic search can actually understand that these have the same meaning and returning us the results. So let's see how it works. Let's assume that we have the generative AI application, and our user is now query what is the next quest to start, when it should supposed to start. So what we are going to do, we are going to query the foundation model and to ask them when the next quest is going to start. This is a bit costly and expensive from both cost and performance perspective. But once we receive the data, we can return it to the client itself. Now let's assume that I'm adding ElastiCache into the architecture. I'm using the vector search here. And the user now tried to generate the same question for my application. But before that, I'm going to use the Amazon Titan to generate for me the embedding vector. Once I have the vector itself, I can fetch the item, the data, from my ElastiCache vector search. Because this is the first time I don't have the data yet on my cache, I'm going to receive a cache miss. And now I need to go again to my foundation model, ask the question, and get back the response. But this time, I store the item on my cache for a warning for the next time I'm going to read it. But let's make it even more cool, more complex. And now I'm receiving similar query, not exact the same query. And we can understand that traditional caching will not work in that way. We cannot just store the data on the cache and expect it to be as a cache hit in the next iteration. And for that, we have the vector search. So let's go through the flow. We go to the generative AI. Then we create the embedding vector. Once we generate the embedding vector, now with a different question, we are asking the ElastiCache vector search. But this time, we're going to receive a cache hit because contextually, it understands that they have the same context. And with that way, we are saving the need to go to foundation model, which is expensive, both from cost and performance. Let's go through the API itself and see how it works. So I'm using here the ftcreate to create the index itself. I'm going to use hash. I can use also JSON to store the data, but here I'm showing an example of hash. We are using the HSNW as the algorithm because it works well in high-dimensional space while very optimized for performance. I'm going to use here dimensions of 128. In my previous example, I showed you only 3, but here I'm going to use more dimensions. And I'm going to use this distance metric, the cosine algorithm. Now, to search the item, I'm using the closest neighbors retrieve, only 10 in that example, from my vector search. Now, I have another option that I can filter out some of the results on the fly, on the server side, and for that, I'm using the index. Here in that example, I'm using filtering only for per country. So in this code that I'm going to show you, we populate the vector store in the text data that build the foundation of the semantic search body. So first, we're going to load the text data and to split it into chunks. And we're going to use for that, we're going to use the LangChain library. Next, we're going to use the chunk that converted into embedding using the embedding model. And we are using the vector Titan to use the embedded vectors. And to query the data, we're going to use the ftcreate that we use for ftcreate. We're going to store it first on the vector search. So to fetch the item, to fetch the data, we're going to use the ftsearch. And we use the same here. We're going to use the closest neighbors. Here we're using only 3. And once we have it, we can search the item on the vector search itself. Now I want to call to Kevin to continue with more advanced use cases. Thank you.
Cool. Let's talk about some additional data structures that you can do in Valkey, starting with one of the functionalities of publish and subscribing. So Valkey, as we talked about before, is a rich data structure server, and with our MMORPG, we want to be able to answer questions about an in-game chat. We want to build a chat functionality for our game, where players can join and participate in an in-game chat that's ephemeral. So let's say here we have a Shadow Dragons guild and a bunch of users that want to participate and communicate with each other. For that, we can use this pub/subs feature within Valkey. So if you're not familiar with the pub/sub pattern, it's a messaging pattern where there are publishers of messages that are decoupled from the subscribers. So a subscriber comes in and subscribes to a named topic. So let's say our topic here is just Shadow Dragons. And a user can come in and say, I want to listen to messages on this topic. Another user can come and publish messages to those topics. And so I can come say hello, and then anyone that's subscribed to that topic will get those messages. So how does this work inside Valkey? So the data here is ephemeral. Valkey is basically just used as a messaging bus so that the data is relayed from producers to consumers directly. It's not stored in memory other than for the transition between the producer and consumer. It allows at most once delivery. So if you're not listening to the topic, then you'll miss the message. There is, however, another data structure that we're not going to go into today called streams that allows you to store messages inside Valkey in memory for long-term storage, and has a number of other rich features such as consumer groups to be able to resume where you left off. But PubSub is our choice for this since a chat message is just ephemeral here. So there's two different types of PubSub in Valkey. One is what I call classic PubSub, and one is sharded PubSub, which is relatively new. We recommend using sharded PubSub because it has better scalability properties. So in classic PubSub, all of the messages that you send are forwarded to all of the nodes in the cluster. So you kind of have this large fan out, and that means any subscriber can go to any node and get all of the messages on a topic. But of course, that doesn't scale as well as you have very high volume PubSub traffic. Whereas with sharded PubSub, just like with the sharded key space in cluster mode enabled, it goes to a particular shard, and all of the producers and consumers know which shard to go to, and so the fan out is much smaller. The main downside of using sharded PubSub is it doesn't support these wildcard identifiers, so you can't subscribe to a large number of topics. You have to do a specific name topic so that you get hashed to the right shard. So how does this work in practice? How do you actually do it? Let's say we have two users here, like we had before of Alice and Bob, and they want to join this and participate in this chat room. So for sharded PubSub, we'll use this subscribe command for Alice to subscribe, and we'll prefix our key name here with chat and then Shadow Dragons being the name. It'll return back the identifier of the topic, as well as a 1 saying it's successfully subscribed. Now, Alice can publish, it doesn't have to be subscribed, but she can publish to this message, and we're going to use, we can do any sort of string to publish to a topic, but here we'll format it in JSON, so it has enough metadata to render the chat in the application. So we'll do publish. We'll get back a 1 saying it's been successfully done, and then immediately after that, we would get this message because Alice is also subscribed to that topic. And the message has in it the topic that it was published to, as well as the actual message that the publisher sent. Meanwhile, Bob can come along and subscribe to it, similar to how Alice did, and then do a publish just before, saying Bob here, and then that message shows up on both of them because they're both subscribed at the same time. And so you can build pretty rich applications this way. It doesn't require a whole lot of memory since these messages are just stored transiently and relayed to the subscribers. Next, let's look at a couple of different probabilistic data structures that we'll talk about in Valkey. Valkey, of course, is an in-memory data structure server, so storage matters. You don't want to have to store a large amount of data if you don't have to. And there are some applications in our MMORPG where accuracy doesn't really isn't paramount, and so we can get away with answers that are perhaps off by a bit. So one such example is a unique user count. So say we want to keep track of how many unique daily active users are playing our game. Of course, we can do a counter and get non-unique users, but we want to do something that is a little bit more advanced. And so normally, let's say we want to do it on a day-by-day basis. We have 4 different users here that are playing our game. And traditionally, if you just were to use a set data structure, it would take O of n space. We would store all of the different usernames or user IDs that are associated with that counter, and then we could just take the set, and that way we'd ensure uniqueness. But within Valkey, there's a data structure called a hyperlog, and this can approximate set cardinality. So it can answer the question of how many unique users you might see. The advantage here is it doesn't take linear space. It is bounded to 12 kilobytes in Valkey, and it has a less than 1% standard error rate, which is pretty remarkable. So how exactly does it and it allows constant time operations because it is small, so it doesn't require O of n space or log n access. So what is the intuition behind how hyperlog works? So say these are some poorly drawn coins that we're flipping. If I tell you I'm flipping a bunch of coins, but I get 5 heads in a row, it's likely that I flipped a bunch of coins in order to see a sequence of 5 heads in a row. And this is sort of the intuition behind how the algorithm works, is it takes these values, observes them, and then it counts the repeating patterns that are less and less likely over time. So what does that exactly mean? The algorithm of hyperlog takes your user or whatever string that you want to be able to count, and it runs it through this murmur hash, which produces a 64-bit uniformly distributed binary string. So it's just a what seemingly random value of zeros and ones. And in Valkey, it takes the first 14 bits of that binary value and computes a hash bucket out of it. So there's 16,000 buckets that can be computed within the hyperlog log. And then the remaining digits, it takes and it counts the number of leading zeros. And this is the analogy of coin flips. The larger number of leading zeros that are happening in this uniformly distributed binary string, the more values you may have seen in order to observe that pattern. And what it does is it takes the bucket and then the number of leading zeros, and it stores the maximum number of leading zeros per bucket that it has observed in the sequence of strings that are being added to it. And then it takes the harmonic mean of this overall. So it's a mathematical equation to basically identify the total number of observations. Luckily, you don't have to actually deal with any of that math when you're using the hyperlog log in Valkey. It has a pretty simple API to interact with it, which is just these pf prefix, and pf add will add a number of items into a particular hyperlog log. So say we want to name it daily active users with the date. We can add 3 to it. We'll get back a 1 saying it's been successful. And if we issue a count command, then we'll get back 3 in this case. And if we were to try and add the same user, it'll come up with the same hash. It shouldn't modify it. We'll get back a 0 saying it has been unsuccessful. And the count is unchanged in this case. There's some other interesting properties here too. So say we want to be able to subdivide it. We now want to, instead of just doing daily active users over the entire MMORPG, we want to kind of partition it into different games. So we can add the 3 users to game 1, and maybe just Alice and Doris to game 2 here. So they're different hyperlog logs. Hyperlog logs are composable, so we can use this command called pfmerge, where we can take the 2 of them, and it basically goes through in that data structure we talked about and just updates the max number of leading zeros based off of the number in each bucket, and it allows you to then get a total sum of unique users across multiple hyperlog logs. So in this case, we have only 4 unique users, even though we've had 5 different observations. So we'll get back a 4 when we count that aggregated hyperlog log. So I ran a quick little simulation of the memory usage and error rate of a set and a hyperlog log. So in adding 10,000 numbers to a set, you'd get back 10,000 exactly because it's storing every single number in the string and then calculating that cardinality. But the memory usage of the set, as calculated by Valkey, is about 420 kilobytes. Whereas if doing the same thing with a hyperlog log, I got back 9,987, so a 0.13% error. But the memory usage here is 12 kilobytes. So you can see that that 12 kilobytes will not expand beyond that. It's the maximum size of the hyperlog log, but the set usage would increase with the number of unique users that get added. Next, let's answer a slightly different question of whether two players know each other. So say you want to keep track in your game, whether you've observed or interacted with a player before. It basically forms this graph that you'd have to keep track of the different users that have engaged with each other, which you could store in Valkey with sets again. We have the different interactions for each individual player. The downside, of course, is that this is also O of n storage space. So can we do better than that? Can we not have to store all of these sort of combinations? And with that, we can use a Bloom filter, which is a relatively recent data structure added to Valkey. And this answers a different question. It answers the membership testing question. So whether a given user has interacted with the particular user that you're querying for. This can result in over 90% memory usage savings over a set, depending on your configuration. Unlike the hyperlog log, this has some configuration options. It has this tunable false positive rate that you're able to tune. The lower the false positive rate, the higher the memory usage of that data structure. But by default, it's a 1% false positive rate. So that the error that you can get is that you would have interacted with someone when in reality you hadn't done that. This is also a constant time operation. It uses a number of different hash functions, which we'll see in a minute, in order to test and to add members to this set. But it's typically a relatively small constant time. So how does this work under the cover? So the intuition is that you have this fixed size bit array that has a number of different hash functions that operate on it. So say for this example, we have 10 bits here, and we want to add Bob to it. So let's say we just have two hash functions. We'll calculate the hash 1 of Bob, and then modulo it by the number of bits. And we get bit number 5. We'll go and update that in our bit array. And we'll do the same thing with the second hash function here, which is another unique hash function. We'll get the value of 9, and we'll update those too. And we can do the same thing with Alice. With every one that we add, goes through the same function. It uses this murmur hash as well. We can update Alice here. There's conflict. You get back 5, and 5 is already 1. We don't do anything with it. And let's say hash 2 of Alice is the first position, and so we'll go and update that. Let's go back 1 second. So the actual when you go and test membership, it goes through the same exact process too. So say we want to check to see if someone else is present, we will go through and observe whether the bits that are hashed are 1 or 0. And this is why, because the hash function is non-unique, you can have false positives. So in this case, we can see that Alice was not previously added. That first bit is a 0. But if, for example, you get back position bit 5 and bit 9 for another user, then you might have a false positive where it conflicted with Bob. So if they're all 0, or at least 1 0, then it was definitely never added to the set. But if all of the values that we look at are 1, then it was maybe added to the set previously. So we don't have to actually store the underlying strings, just basically some representation of the hashed value. So the memory usage savings are pretty significant here. So if you look at a 1% false positive rate, you can get about 112 million items with 128 megabytes, or scaling linearly 448 million items with 512. And if you were to drop the false positive rate to 0.1%, then you can get, using the same memory usage, you have still a relatively large capacity, 74 million with 128 megs, or 298 million with 512. And of course, you can kind of tune this as your needs fit. How do you actually use this in Valkey? So again, it has a relatively simple API where you can just interact with it as you would a set. So there's this bf.add command, which allows you to add strings into a given Bloom filter. We get back a 1 here saying Bob has been added. We can similarly add multiple users simultaneously, atomically, to the interactions here. And then this exists is the membership testing command, where you can just test if a given user was there. We'll get back a 0. However, and Bob, of course, would return back 1, saying that it does exist, it has been added. But what can happen is that you get back a false positive here. So we're testing whether Frank has been added to the interactions with Alice, but we get it will conflict in this case with either Bob, Charlie, or Doris's hash values, and we get back a 1. So let's move on to another data structure within Valkey that can keep track of geospatial data. So let's say we are managing our MMORPG and we have this virtual rich world where users are in different locations, and we want to see which users and points of interest are located near a given user at a point in time. And for this we can use the Valkey's geospatial commands. So what is geospatial? And how does it work? So in Valkey, you would map first with a latitude and longitude. Basically, you would take your virtual world and divide it into a normal grid here. That latitude, longitude that you store as input is taken into a geohash algorithm and stored as a traditional geohash, which it works by sort of subdividing the world into smaller and smaller grids. And it generates this normal geohash is a string of characters. We would take it into a sort of this 52-bit integer. And the properties of the integer are interesting in that the closer these numbers are, the closer they are in location to each other because of the way that it interleaves the latitude and longitude. And this has the nice property that you can kind of use it as a score. So things that are close to each other and numerically are close to each other in latitude and longitude. And so this score is then fed into another data structure within Valkey called a sorted set. Sorted sets are often used for things like leaderboards, where you just have high scores. You want to be able to keep track of like the top N. In this case, the sorted set is actually used to query things that are nearby a given latitude and longitude. However, it has some convenience functions on top of it. So this allows you to do sort of bounding box and radius querying in O of log n time. So how would you actually use it in practice? So let's see how it works. You'd have these geoadd commands, so it has these convenience functions on top of the sorted set. You can do a geoadd with different latitude and longitude. Here we're adding Alice, as well as a point of interest of the beach down here on the bottom. We'll get back a 1 saying it's been successfully added. And then let's say we have another player here that wants to query for the points of interest around them. So you use this georadius command and you query the map. It has a slightly different latitude and longitude, so it can do different radii here. So let's say we do a 3-kilometer radius. We would get back both items that we've added here, Alice as well as the beach at the bottom. However, if we were to do a smaller radius here, just a 1-kilometer radius along that point, we would just get back Alice. So you can use it to query things around it. You can then use it to kind of filter further, so that you can query the distance between any 2 points in that as well, and get it back in a number of different units. So say we want to see the distance between Alice and Beach 1 in meters, and get back that it's about 1,600 meters between them. So you can use it to further filter the results of the radius if you want to do things like bounding boxes. Now let's look at a usage of rate limiting in our application. So you might want to use rate limiting in an MMORPG to enforce game mechanics here. So let's say we want to answer the question, does a player have enough stamina to cast a given spell at a point in time? So as Bob is trying to access a resource, in this case spell casting, and can only do so many spells in a certain time period before that quota resets. So we can do this simply in Valkey using a counter effectively. And the string data type here can be used to also support numerical operations. So you have some increment and decrement commands in Valkey to manipulate numbers. So if I were to increment just a given counter here, it'll create it and set it to 1. And I can further manipulate that, and if I increment it again, it'll go to 2. And this is, of course, a constant time operation that you're performing. So we can use this to build a rate limiter for Valkey, for our application. So let's say we want to be able to start our counter here at 0 and allow 3 requests until a given time delay is up. So you just have three requests, let's say in like a 5-second period. So what we can do is we can start our counter and use a Lua script to do this atomic logic to be able to count, return back a value, and then make sure it expires at the end of that time period. So we'll use a TTL basically to reset our rate limiter at the end of the duration. So just looking at this numerically, users trying to offer requests, we'll count up to 3 here, and then once it gets to 3, no more requests are allowed until the TTL fires. As soon as the TTL fires, that item is basically removed from the cache, and then that same process can restart again as if the user has sufficient credits. So let's walk through that Lua script to see how it works. So as I said, Valkey supports some simple scripting operations where you can do compound operations atomically in a Lua script. Lua is a language that you might not be familiar with, but it's relatively straightforward. It can interact with the server commands and do simple logic on top of it. So let's say we have a couple different globals here in our script. We want to set our limit to 3, and our expire time would be 4 seconds in this case. We'll start by fetching the key that we're operating on, in this case the given user's stamina, and we'll fetch it from the Valkey server that we're running on. If it doesn't exist, meaning that it hasn't either has been evicted or it's starting from scratch, then we'll set it to 0 and set the expiry time to 4 seconds. And if it does exist, then we have already previously fetched the value. And then we just check if we're within our limit. If we are, then we'll be able to increment the key and return 1, saying that the user is allowed to cast the spell. Otherwise, we'll return 0. So this is sufficient to build a simple rate limiter that just allows a specific number. But let's say we want to have something that's a little bit more. Well, let's see how you actually use it too. So we can load this script first by just inserting it into Valkey. We can do script load and put that entire string that you just saw before into the server, which then gives you back this SHA ID. This is the unique identifier hash value of the script that you can then use in subsequent requests to invoke that script. So then you can do eval SHA, the script ID, and then pass it the arguments here. Like we saw before, we want to give it the key name, the number of spells that Bob has placed in this particular example, and it will then return back a 1 or a 0, whether that is an allowed spell or a disallowed spell. This is relatively simple, but let's say we want to have spells that have different types of different costs. So it can do a simple spell or a more complex spell. So our previous example wouldn't have worked with that because it just allows a simple counter. And with this, we can do a token bucket, which is a little bit more advanced rate limiting algorithm, where you have a given capacity and refill rate of that bucket. And if the bucket has enough credits for your given spell, we'll subtract from it. Otherwise, it will be disallowed. So we keep track of a little bit more metadata associated with a given user's spell count here. We can do this in Valkey by using the hash data structure that Yaron talked about earlier. And for this, we need to keep track of 2 different pieces of information. One is the number of tokens that are currently in the bucket, and 2 is the last time we updated or touched that bucket. And you need the timestamp because tokens accrue over time, and so you can calculate the difference there. So let's break down what the script looks like in this scenario. Still using Lua script, but it's a little bit more complex. So we can look at some advanced Lua scripting here. So rather than having hard-coded values, like global values in the script before, we're going to take in these values as arguments here. So we have the bucket size and the refill rate as arguments to the script, as well as the number of tokens for the given request, and we still get the key out. So the first thing we need to do is get the value of the hash, which may or may not exist if we haven't run this before. So we'll fetch using hmget, as well as the current time, which is a command within Valkey. The first step is to refill the bucket. So we check to see if there was an update time, and if that exists, then we'll go ahead and calculate the difference in terms of credits. We'll refill the bucket as the first step, and this means you don't have to be running this periodically. You can just run it any time that you need to query it, and it will refill the bucket up to the max size. If the bucket's already at the max size, then or if it's beyond that, then we'll just go and reset it to the max capacity. And then we need to determine if the request is allowed. So if we have enough tokens, if our current token count is more than the number of requested tokens, then we will subtract and allow the request. Otherwise, it will be disallowed and the number of tokens are not updated. And then we'll go and update that data structure to represent the current number of tokens and the last update time. And lastly, we'll do some optimization here. We could keep this hash in the data structure forever, and it'll eventually get updated. But say the user goes away, we want to be able to reap these at some point in time. And so we can, again, use a TTL to expire this hash data structure at the point where basically it would have reached the ceiling of the bucket capacity anyway. And so we'll take the bucket size by the refill rate and just expire it at that point in time. And with that, I wanted to thank you for coming, and we'll be available off the side here to answer any questions that you may have about Valkey or data structure modeling. Thank you so much.